Hello, good people. Welcome to video number 1 of section 10.12, the Lagrange error bound. The Lagrange error bound. What the heck is that? I will admit right off the start here that the Lagrange error bound is one of the most skipped parts of the AP exam. Usually, when it appears, it's one part of a free response question. Um, And some students, when they get to it, realize that they can skip it and gain points elsewhere. And I'm not saying you should do that. I will always encourage you to read the problem. And if it's set up in a way where you can do it and you can do it quickly and correctly, by all means, do it. Um, and for some reason, this is an area where students struggle, and quite frankly, some teachers struggle as well. The idea, however, is pretty straightforward. And if you look at this graphic, I think the idea is captured perfectly right here, which is to say this. In the previous section, we were looking at doing some Taylor approximations, Maclaurin approximations, as a way to estimate actual values, right? So when we look at exact functions, we usually are trying to approximate non-algebraic functions. Non-algebraic functions would be like sine x, cosine x, e to the x, the natural log of x. These functions are what we call transcendental. Transcendental. Meaning they can't be solved. If I were to have some kind of trig or exponential or natural log equation, I wouldn't be able to solve it with my algebraic methods of addition, subtraction, multiplication, division, right? There's another way to solve them. And sometimes using a calculator is our best way to solve them. And so some people call these functions like um, difficult functions or ugly functions because they don't behave in a very algebraic four function way. And so these are usually the functions that we try to estimate. Now, going back, if my function value is what I'm trying to find, and that's the exact value, I can use a Taylor or Maclaurin polynomial to estimate it. But if I'm estimating it, that means there's a leftover, right? There's something that didn't complete the exact value. And so therefore, this remainder is what we base the idea of this error on, that if I were to subtract the original or the exact value minus my estimate or my approximation, then the difference here is the error. And that error is this remainder, the leftover that I'm missing that would make it complete. So Taylor's theorem says there most certainly is a remainder whenever I use a polynomial approximation. So this is my approximation. Taylor's formula says the approximation, however far you went, right? You could have gone to the second degree term or the nth degree term, whatever degree term, but you didn't go all the way. So it's not an exact value. But if you add this remainder, then that's going to equal the exact function value that you were looking for. Lagrange goes further and he says, yes, and maybe he took some improv lessons. Yes, and this formula is a way to find that remainder. So the Lagrange error, is a way to find the remainder that if I added it to my approximation would give me the exact value. Now, if you look at the formula should look familiar because it's really just the next term in the sequence, but with a twist. So notice, however far out you go, so let's say you go out to the second degree term where it's being squared, this would go out to the third degree, right? It would be n plus 1. However far your approximation goes, this goes one step further, and here's the key. The derivative at that term is evaluated at this z value. So Lagrange is saying there's this special number that exists that if you take the n plus 1th derivative and divide it by n plus 1 factorial and multiply it times the x value that you were trying to find minus the center to the n plus 1 power, you're going to get the exact remainder that was missing that made that would make that approximation equal the original function. Now, what is this magical z value? Well, it's a value, and it says right here there exists a z value between x and c. So the z value is trapped between the center and the x value that I'm trying to evaluate. Well, where is it? Well, we don't know. And sometimes it's difficult to find. I mean, that's like finding a needle in a haystack, right? I'm trying to look for a number, this exact perfect number that's allegedly between my center value and my x value, that when I take the n plus 1th derivative and do all this stuff, it's going to give me the exact remainder that is missing from my approximation. Well, Taylor comes back and Taylor says, why don't we create a bound? Because finding the remainder is going to be difficult. Why don't we create a bound? Because if we can find a maximum value of what the n plus 1th derivative at that z value should be, well, then that would certainly create an upper bound of my remainder value. So notice the change. Lagrange says, hey, the remainder equals this thing exactly. Taylor comes back and he says, true, and because it's hard to figure out that z value, why don't we just say the remainder has to be less than or equal to whatever the maximum is of the n plus 1th term at that z value. So if I can figure out a maximum value, then that's going to create an upper bound, and I know that my error is going to be under that. So it's almost like we're estimating the error of the approximation of the value. Okay. Notice the wording here also. It says the notation, the max of f of n plus 1 at z represents the largest value of the n plus 1th derivative at z will take on a z that will typically lie between the center point and the x value. Typically lie between them. Okay, so let's look at an example to see how this works. And example one, they do me a favor and they give me, luckily, I pressed something that made things disappear. Let's see if they come back. I think my computer is probably as confused and tired as you are. But we're going to get to it. There it is. So somebody did me a favor. Okay, I think my computer is really tired. It keeps going and resetting. Here we go. I'm going to try that again. And we're going to try that again. There you go. Example one. Someone did me a favor and they found the third Maclaurin polynomial. If it's Maclaurin, that means I know my center is 0. Okay. What are we approximating? Well, we're approximating sine of x. Okay. And if it's the third Maclaurin polynomial, somebody found it for me. Perfect. What am I supposed to do? Use Taylor's theorem to approximate sine of 0.1 by using the third Maclaurin polynomial. Well, let us begin. I'm going to approximate sine of 0.1. I'm going to approximate. Make sure you use proper symbols. This is not equal. This is an approximation. By using p of 3 at 0.1, which is 0.1 minus 0.1 to the third over 3 factorial. Okay, so I could use my calculator and get this, but I noticed that since I'm using point 0.1, it's maybe easier to use to convert it to fractions. So point 0.1, that's 1/10, minus point 0.1 to the third power, that's point 0.1 times point 0.1 times point 0.1, that's 0.001, which is 1,000th, times 1 over 3 factorial. Remember, 3 factorial is 3 times 2 times 1, so that's 1/6. So this is really 1/10 minus 1/6000th. The common denominator is going to be 6,000. Let's see, I need to multiply 10 times 600 to get 6,000. So that's going to be 600 minus 1. So that's 599 over 6,000. I believe that's the estimate that we're doing. Now, we're gonna figure out whether that's a good estimate or not. But we're gonna determine the accuracy of this approximation. I do want to point out we have a calculator, right? So we could do sine of 0.1 and get an answer. And I could do the 599 divided by 6,000 and get an answer and realize, hey, those answers are pretty darn good, right? One, two, three, four, five, 6 decimal places. That's a pretty accurate estimate. It's not until the 7th decimal place that they start to defer. But everything else in the first 5, in the first 6, I'm sorry, in the first 6 decimal places, everything matches from what the calculator is telling me sine of point 0.1 is with what my approximation was using the third degree Maclaurin polynomial. So that's pretty good. Okay, but now let's look at the accuracy of the approximation. Okay, so how are we going to do that? Well, according to this, my error, my remainder, for the nth, that would be the third, at x value, my x value was 0.1, has to be less than or equal to the absolute value of the maximum of. Now remember, I'm supposed to take the n plus 1th derivative. So wherever I stopped, and I stopped at the third degree, I'm supposed to go one more. So I'm supposed to take the 4th derivative at z, at this z value, which I don't know what that is, but I'll come back, over 4 factorial. Why not n plus 1? You could say n is 3 and 3 plus 1 is 4, so that would be 4 factorial, times my x value, which was zero point 0.1, minus my c value, which was the center point, which is 0, to the n plus 1th, which would be the 4th power. Take the absolute value of that. So I'm saying the remainder is less than or equal to this setup. Well, 4 factorial, that's 4 times 3 times 2 times 1, that is 24. And 0.1 minus 0, that's just 0.1 to the 4th. That's 0.1 times 0.1 times, that's 1/10,000th. A 1 with 4 zeros after it, so 1/10,000th. So I got that. And if I really, really wanted to, I guess I can multiply these two and just get 24 thousandths. And so here's what I'm left with after doing all of that. But I still don't know what the 4th derivative of f is, and I don't know what the maximum of the 4th derivative of z is. So let's go back. If f was sine, f prime was cosine, f double prime was negative sine, and f triple prime was negative cosine. And the 4th derivative would be the derivative of that, which would take me back to sine x. So really, I'm looking for the maximum of the sine of this z value. Now remember, we were told z had to be in a specific range, right? Z, where can I write it? I guess I'll write it over here. Z had to be between my center point and my x value. Well, that's a lot of numbers in between 0 and point 0.1 because I can choose any decimal, and I'm looking for the maximum. Hmm. Well, now I'm a little bummed because how do I find the maximum of sine of z? Well, remember what sine looks like. Sine looks like this, starting at 0. Oh, wait, from 0 to point 0.1. So from 0 to point 0.1, remember that the height is pi over 2, which is 3.14 divided by 2. So that's about 1.57. So point 0.1, I don't know, is somewhere here. So if I look at this carefully, this would be the maximum, right? Between 0 and point 0.1. Well, point 0.1 is higher than 0. But what is the value there? The value there is sine of point 0.1. Well, wait a minute. Isn't that what I'm trying to estimate? Well, now I'm just going in circles. What the heck? Except, if you read this little green box, it tells you something that you can do. Remember, we said that the z will typically lie between the center point and the x value. But if I look at my graph, I can guarantee any amount of money that you want. I can guarantee that the highest the sine of any z value is going to go is this peak at pi over 2. What is the maximum value for a sine function? The highest sine is going to go, the biggest sine value I can find on the unit circle is 1. So why don't I just say that the maximum of sine z, well, yes, it should be this point, but I have no idea what that point is. So why don't we just say the maximum of sine of point 0.1 is 1? And so therefore, my estimate that I found here in the box, so this was my approximation, it is definitely the approximation accuracy. The remainder, the error, is less than or equal to 1 over 24 thousandths. I put an extra 0 there. I don't know why. 1 over 24,000. That is the error that I can guarantee that my approximation is good for. That accuracy. It has to be off by no more than 1 over 24 thousandths. And that's a pretty good approximation. Now, this is really technical. This is, to some extent, really theoretical. And as we do more of these, you're going to find that some of these are a little head scratching and maybe not the most intuitive of the topics that we studied. But what I need you to do is kind of think of the big ideas of what we're doing and try your best to interpret what they're giving you, interpret what they're asking you, and then use those things together to get to the answer. We're going to come back in video number 2. We'll do example number 2, and hopefully it's a little bit more, it gets a little clearer for us.